Thank you everyone for coming. Kia ora, my name is Christina Riesselman, and as Lynn said, I am in both the geology and marine science departments. It's a really nice fit for me because my core research interest is in understanding, apologies, is that better? Is that exactly the same? So my core interest is in using geological materials and specifically marine sediments to understand how the ocean has changed in the past, and most particularly during past intervals of warm climate that are well established in geologic history. So I thought a nice entry point today, and probably a place where we can all come together and have a common understanding, is through the Paris Agreement. So what we're looking at here is a thermometer from the Climate Action Tracker that evaluates all of the signatory nations to the Paris Agreement, evaluates the pledges and targets that they've made toward reducing carbon emissions, and also the track that each of those nations is on with respect to their current carbon mitigation policies. Now, the agreement in Paris was that the globe would work together to make sure that carbon emissions would be reduced sufficiently to keep global warming below 2 degrees C, so that's our little yellow field here, and with a strong intent to limit that warming to less than 1.5 degrees C. This is temperature increases over our pre-industrial baseline, so over the average global temperature before we started emitting CO2 through industrial activities. Now, it turns out that since the Industrial Revolution, we've emitted enough CO2 to raise temperature already by 1.5 degrees. And this is in September of 2020, so that's the most recent sort of synthesis that the Climate Action Tracker has assembled. And as you can see, our current pledges and targets put us up here in what the agreement, or what the Action Tracker would characterize as an insufficient range of response or of action. And then the current policies that are, that are in place in all of the nations that have signed on to the Paris Agreement would actually allow global average temperature to rise by 2.9 degrees C, and I guess this is a mid-projection, so somewhere between 2.1 and 3.9 degrees C over pre-industrial averages. So in order to accomplish these limits, so now we're looking here, another figure, again, from September of this year from the Climate Action Tracker. So we're looking at global greenhouse gas emissions, our historical emissions track since 1990, coming forward to 2020, and then a series of projections based on different behaviors and different sets of policies by the signatory nations. And what you'll see is that in order for our global temperatures to remain within this sort of Paris target range, we need to, so we're looking at greenhouse gas emissions in gigatons of carbon dioxide per year. Currently, our global collective emissions are around 50 gigatons per year. And we actually need to reduce our emissions functionally to zero in order to reach these climate targets, or even to find technologies that allow us to remove some of the current CO2 burden in the atmosphere from the atmosphere. So for me as a geoscientist, this is a really interesting problem because you actually have to look quite far into the geologic past to find a climate where atmospheric CO2 was at our present level a bit above 400 parts per million. And so what we'll do today, what I'll do with you for the rest of my time, is walk you through what the planet looked like the last time our CO2 levels were where we sit today. And I think convince you that it's really essential for us as a global community to find policies that let us reach these targets. So with thanks to Chris, those of you who are here for the morning session, you'll already have your eye dialed in to some of these paleoclimate graphs. I'm a graphs and facts person here. So on this figure, this is the only one we'll look at today that's organized this way. We have today right here at 0. So our current atmospheric CO2 level is right up here, right around 412 parts per million. And you can see these very rhythmically paced glacial interglacial cycles going back through time to about 800,000 years, right? So climate has transitioned in and out of glacial, sort of a glacial period and into an interglacial, like our present climate system, on about 100,000 year heartbeat over the last million years or so, right? But you can see that at no time over that last million years has CO2, atmospheric CO2, so we're looking at the temperature on East Antarctica here on our red curve, and these are anomalies relative to today. So we have a few times when temperature's been a little bit warmer than present, but at no point, so these are CO2 reconstructions from ice cores, at no point has atmospheric CO2 come anywhere close to where we sit today. Now, the thing that's the sort of the heartbeat of that climate, of those glacial interglacial cycles over the last million years, and going back even further than that, have been these changes in the shape of Earth's orbit and the angle of our axis relative to the sun. So those are, they're predictable. We can reconstruct, or physicists, people smarter than me, can reconstruct what those have looked like going back to at least 56 million years. So we have a very good handle on how these subtle changes in the way solar radiation reaches the surface of the Earth, how those contribute to changes in climate. This is the one presently that's driving most of our cycles. You go back, so this is whether the Earth's orbit is more circular or more elliptical going around the sun. If you reach back longer than a million years, we come into a planet where the amount of tilt, so the Earth's axis just tick-tocks up and down, a little bit like a metronome, right? And where the degree of tilt was the thing that dominated Earth's climate. Now, this is a lot of wiggles, but I'll walk you through what we have. I showed you here that we see no time in the last 800,000 years when CO2 has come close to our present level. And in fact, in order to find a time when atmospheric CO2 was elevated above 400 parts per million, we have to track back here to 3 million years ago. So every set of wiggles I'll show you for the rest of the day will have today over here at the left and older times going along to the right. And these are a bunch of different approaches to reconstructing the amount of carbon dioxide in the atmosphere. I won't belabor these different approaches. The important thing to note is that we have this handy time right around 3 million years ago when CO2 was where we sit today. Down here we have, you can see some zigzags. They're a little bit faint on this projector, but these are the same series of glacial interglacial cycles that you saw in the ice core record, this time preserved in little amoeba that grow calcite shells and live on the seafloor. So those are a really nice shorthand for how climate has changed over geologic time. This is pretty much a paleoclimatologist's roadmap to how climate has evolved, right? So where we see higher values, we're looking at warmer conditions with less ice on the planet. Where we see lower values, this is in the oxygen isotopic composition of those microscopic organisms, those forams. Where we see lower values, we know that we had a cooler deep ocean or more ice on the planet. They have sort of an additive effect. So this time, about 3 million years ago, happens to be a really nice analog for future climate for a number of reasons. One biggie was that the continents and ocean basins were in roughly the same place they are today. So that means that circulation was very similar. We know that the northern hemisphere was largely unglaciated, which sadly is a condition we're moving toward right now. Sea level was between 22 or around 22 meters higher than present, which is really significant, right? That's a range of change that's truly outside the comprehension of most policymakers. And then many modern plants and animals had evolved by the time we enter this analog interval, which is useful if we want to use those as proxies to tell us how climate has behaved in the past. Now, the importance of this interval to Antarctica was first identified through a set of controversial microfossils found in the Transantarctic Mountains by this man, David Harwood, who was an undergraduate mentor of mine, and the person, coincidentally, who turned me from an English major into a geologist. And these microfossils came from quite high in the Transantarctic Mountains. And the reason they were controversial is because they were collected from these basins in the interior of East Antarctica, where we presently have about 3 kilometers of ice sitting today. And they're pretty diagnostic of age, right? So we have some species here that were alive between about 3.3 and 2.7 million years ago. And all of these, as Pete highlighted, are phytoplankton All of these, as Pete highlighted, are phytoplankton, which means that they require sunlight to live, and they also require sort of an open surface ocean, right? So in order to emplace fossils like this at an elevation in a location like that requires quite a change in the climate. So this was controversial at the time. So we have an indication that for some reason, around 3 million years ago, these warm fossils were living in or near this part of Antarctica. And prior to that discovery, the assumption had been that East Antarctica, which I think I can show you next, that East Antarctica over here had been in its present glacial state for about 14 million years, right? So understanding whether this part of the Antarctic ice sheet, which contains about 53 meters equivalent sea level, whether any part of that was unstable the last time atmospheric carbon dioxide reached 400 parts per million, turns out to be quite a fundamental scientific question. And now I don't have a ton of time, so we're going to get to the meat in a slightly glossy way. All right, so if you strip away the East Antarctic ice sheet, you'll see that we have subglacial basins. So here, our green colors are sea level. Anything that's in hot colors is where the bedrock is above sea level. Anything that's in blue cold colors is where the bedrock is below sea level. And it turns out that a great deal of the Antarctic ice sheet is sitting on ground below sea level. And that makes it vulnerable. So here we have a cross section going from right about over here across the Ross Ice Shelf and then out through one of these subglacial basins in the East Antarctic. Turns out that where your ice is grounded below sea level, it's quite susceptible to warm ocean water coming into proximity to it and can eat away at the foot of an ice sheet, right? So this time 3 million years ago has been an area of intensive research interest. Over here, we have a global compilation for that specific little snapshot in time. This is only for interglacial periods. And you can see, this is an anomaly plot. So around the globe, for the most part, every place in the deep ocean, or this is a surface ocean reconstruction. Every place in the surface ocean was warmer than present by somewhere on the order of, if we look in the Southern Ocean, on the order of about 2 to 2.5 degrees C. So that means that around Antarctica, we have ocean water up to 2 degrees warmer than present coming into proximity with the ice sheet. So I'll take you now to a little site sort of just off the margin of one of those subglacial basins. It's this site over here. And the important thing to note about it is that it's 8 degrees south of the modern polar front. So if we zoom into that site, using the drill ship of the International Ocean Discovery Program, we have sediments represented at the bottom. We recover sediment cores. And then in those sediment cores, we can access these microscopic fossil diatoms. So these are very environmentally sensitive, and they have quite specific environmental preferences. So we can use the distribution of different species of diatoms in different intervals of interglacial material. So the green stuff here represents material deposited when the ocean was open. We can use those species to understand how climate has evolved in the past. So here we'll focus just on these two interglacial intervals. So here the brown colors represent glacial sediments. The green are interglacial sediments. And if we look at the diatoms through this sequence, you can see that we have a group of species with preference for open ocean conditions. We have a group of species with an affinity for sea ice. And then we have this couple of species with a preference for subantarctic conditions that happen to pop in just in these two interglacials associated with that most recent interval of 400 parts per million atmospheric CO2. So what does this mean? We have a big glaciation leading into that and sort of overall cooling. But if we really zoom in to those two interglacials, you can see that these, particularly this one, is associated with a specific marine isotope stage recognized to be quite a good analog for our present climate. So once we identify the presence of subantarctic taxa quite close to the Antarctic continent at this time, we have the opportunity to look at some of these other sites that were part of that big global reconstruction. And when we do that, I've now expanded our record to show you how this hangs on time, and then take the sort of lower resolution records from right around the Indian and Pacific sectors of the Southern Ocean. You can see that this event, this sort of arrival of subantarctic conditions, wraps right around the margin of the continent. So going from sort of a simplified view of today's polar conditions, I'll stop soon. So then if we take that suite of material, we see a considerable contraction of the Southern Ocean frontal system in the Pliocene during that analog interval. That's really important because so now we're looking at the shape of the seabed and the much more complicated package of fronts that circulate around Antarctica. And you can see that at places where we have seafloor ridges, so we have essentially mountain ranges under the ocean, our frontal system bundles together and is pushed really far away from the continent in the current climate. But we know in past climates that frontal system was able to jump beyond these bathymetric limits and enter a configuration where it could snuggle in quite a lot closer to the West Antarctic ice sheet. So I'm gonna hop through a second location that was inside that yellow circle to let you know that at the same time that we saw our fronts contracting, we also have evidence for open ocean conditions in very close to the West Antarctic ice sheet. And those ocean conditions were about 2 degrees C warmer than present, right? So right there inside that acceptable sort of Paris maximum. And what we can learn from that is that with just subtle changes in the Earth's orbit under that sort of Paris acceptable configuration, our Ross Sea sector went from an environment, this is sort of the modern configuration of the McMurdo Sound region of the Ross Sea, so something that looks a little bit like this to something more like that, right? So this is quite an extreme end member possibility, but I think it, it gives us a pretty definitive answer to this question of whether 2 degrees C is too warm for Antarctica. And I would argue that it definitively is. So Antarctica under a 2 degree C Paris Agreement world is a much different place, and a place that has a lot of potential consequence from a sea level perspective for all of us in New Zealand and coastal communities everywhere. That's what I got.